In this video, we're going to introduce rational functions and rational inequalities. So rational functions, the root word of rational, of course, is ratio. So rational function is supposed to be a ratio of something. Now remember, rational numbers are ratios of integers. Rational functions are ratios of polynomials. So we have a rational function as p of x over q of x, where p and q are both polynomials. And of course, we don't want q of x just to be the zero polynomial because that would cause some definition issues. All right, so when we talk about the domain of a rational number, well, we know that polynomials are really nice functions. They have domains that are all real numbers. All the time, polynomials are. Rational functions, almost the same case. It's the set of all real numbers except those where we would make a zero in the denominator. So we can plug anything into that we want to a rational function so long as it doesn't cause a zero in the denominator. And at these values, the function is going to have some sort of a break in it. So let's investigate what this break may be. The break could possibly be a hole, or it could be a vertical asymptote. So let's look at a couple of specific examples. Let's look at the function f of x equals x squared minus 4 over x minus 2. Certainly, the way this function is defined, I cannot plug in 2 for x. I can plug anything else that I want in for x, but not 2. However, if I'm not equal to 2, this actually simplifies. You can factor the top as x plus 2 times x minus 2. And as long as x is not equal to 2, those two x minus 2's would cancel and leave you with x plus 2. So essentially, this function is the line y equals x plus 2, except there's going to be a hole for when x is equal to 2. So we would get this line x plus 2. But I would represent the fact that I cannot plug in 2 into the function by putting in a hole into that line. All right, so notice that when we did this particular example, we ended up factoring the numerator and doing that cancellation. That original function, the x squared minus 4 over x minus 2, would not have been lowest terms because they had a factor in common. So we used the term lowest terms like we do for fractions. So we say that the rational function is in lowest terms if the two polynomials have no factors in common. In the case where we are actually in lowest terms, then any spots left that make the denominator 0 will result in a vertical asymptote for the graph. So let's look at the function f of x equals x plus 3 over x squared minus x minus 2. First thing we're going to do is we're going to factor the denominator. So let's check to see if we're in lowest terms. So we'll factor that denominator. It factors as x plus 1 times x minus 2. Notice they don't have any factors in common on top and bottom. We can check the domain pretty quickly. We notice that negative 1 makes the denominator 0 and 2 makes the denominator 0. So again, owing back to what we talked about on the previous slide, those are two values at which the function will have some sort of a break. But since we're in lowest terms, that break in this case is going to be vertical asymptotes rather than holes in the graph. So we get a vertical asymptote of x equal to negative 1 and a vertical asymptote of x equal to 2. And we see that on the graph here. We've got this vertical line at negative 1 that the function gets close to on the left-hand side and on the right-hand side, and then the same thing with x equal to 2. Remember when we talked about end behavior in a previous video, we can talk about a behavior around a vertical asymptote, much like we talk about end behavior for polynomials. So notice again here that as we get closer and closer to negative 1, as we come in from left to right towards negative 1, the y values increase without bound. They get bigger and bigger and bigger. So this is how we write this in notation. This is as x approaches negative 1, the little superscripted negative sign here means from the left, or from the negative side of negative 1, the left-hand side of negative 1. So this is as x approaches negative 1 from the left, f of x approaches infinity. So again, as we get close to negative 1 from the left-hand side, the y values get arbitrarily large in the positive direction. On the right-hand side, going from right to left, going in from the right-hand side here, the y values are decreasing without bound. The closer we get to -1 on the right-hand side, the bigger the y values get in the negative direction. So we write this as x approaches -1 from the right. That's what the little superscripted plus sign means here. F of x, this should be an arrow. This should be f of x approaches -infinity. This should be an arrow, not an equal sign. We can describe the behavior near x equal to 2 similarly. As x approaches 2 from the left-hand side, the function goes to -infinity. And as x approaches 2 from the right-hand side, the function goes to positive infinity. So let's switch gears a little bit. Instead of talking about vertical asymptotes, let's talk about a couple of other types of asymptotes that a rational function might have, and those are horizontal and oblique asymptotes. So vertical asymptotes occurred where the denominator was 0 and the numerator was not 0 at the same time. Horizontal and oblique asymptotes are descriptions of the end behavior of rational functions in certain situations. So let's talk about what those certain situations are. So in the previous example, the graph of the function got close to the x-axis as x went to positive or negative infinity. Let's just scroll back to that picture. Here is the picture of the original function. Notice as we go out to the left or out to the right, this function is getting closer and closer to the x-axis. Could see this a little bit better if I had a little farther out on the x-axis. But this really does get closer to the x-axis in both directions. So in this case, we would say that the line y equals 0 is a horizontal asymptote. And I apparently put the graph on this particular slide as well. All right, so let's look at another example. Let's consider the function f of x equals x plus 1 over x minus 3. Here's what that particular function would look like. Notice that at 3, we've got that vertical asymptote there because it makes the denominator 0 and does not make the numerator 0. As x goes farther and farther out to the right, or as x goes farther and farther out to the left, we see that the function gets closer and closer to this horizontal line, y equals 1. So in this case, the horizontal asymptote is y equals 1, and we can express this as an end behavior statement, much like what we did for polynomials. As x goes to positive infinity, or as x goes to minus infinity, the function approaches 1 in this case. So we get closer and closer to that value of 1. Generally speaking, for a rational function, if the degree of the numerator is less than the degree of the denominator, then the x-axis is the horizontal asymptote. Y equals 0 is the horizontal asymptote. We saw that in that first example with the x plus 3 over x plus 1 times x minus 2, I believe were the numbers. Anyway, if the degree of the numerator is less than the degree of the denominator, then the x-axis is the horizontal asymptote. If the degree of the numerator and denominator are the same, then you can use the ratio of the leading coefficients to give you the horizontal asymptote. And if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. So let's go back to the previous slide. Notice here on this one, the degree of the top was 1. The degree of the bottom is also 1. So the horizontal asymptote would be 1 over 1. Y equals 1 in that case, which is exactly what we saw. Let's look at another example. Let's say we have the function g of x is 5x cubed minus 7 over negative 2x cubed plus 6x squared plus 4x. The degree of the numerator is 3, and the degree of the denominator is 3. Since those are equal, we can look at the ratio of the leading coefficients and conclude that y equals negative 5/2 is the horizontal asymptote. If we have the function h of x is equal to 5x plus 6 over x to the 4th minus 12, the degree of the numerator is 1, the degree of the denominator is 4, so the degree of the numerator is smaller, which means the horizontal asymptote is the x-axis, is the line y equals 0. If we have the function j of x is equal to x cubed minus 2x all over x, the degree of the numerator is 3, the degree of the denominator is 1. Since the degree of the numerator is bigger there is no horizontal asymptote. So we've talked about vertical and horizontal asymptotes, and I promised that we would talk about oblique asymptotes. That's the special case that we're going to talk about now. This happens when the degree of the numerator is exactly one bigger than the degree of the denominator. Then it has to be exactly one more on top than on bottom. So look at this particular function, x squared plus x plus 1 over x minus 1. The degree of the top is 2. The degree of the bottom is 1. So we have exactly one greater degree on top than we do on bottom. Here's a picture of this particular graph. The line here that's the dashed line, of course, is not actually part of the graph. It's an asymptote. It helps us get a graph of what's going on. So we notice as x gets large, or as x gets small, large in the positive direction or large in the negative direction, the graph approaches this dotted line. This is what we refer to as an oblique asymptote because we have a line here that we do get closer and closer to. It's just not horizontal. We also call this a slant asymptote, so either oblique or slant, either of those words is correct. So we need to go about talking about how we find oblique asymptotes. Well, we do this by polynomial long division. We actually take the top and divide it by the bottom. So the top in this case was x squared plus x plus 1. The bottom was x minus 1. X goes into x squared x times, right? Distribute the x through, we get x squared minus x and have to subtract. X minus a minus x gives us 2x, and bring down the 1. Need to multiply x by 2 to give me 2x. Distribute the 2 through to get 2x minus 2. And again, subtract 1 minus a minus 2 is 3. So using the division algorithm, we've found a quotient and a remainder. So that means we can rewrite our function as x plus 2, the quotient, plus the remainder 3 over what we divided by, the x minus 1. Notice that as x gets large, the 3 over x minus 1 gets closer and closer to 0. The bigger x gets, the smaller this fraction gets. So the outputs get closer and closer to x plus 2, which is why the line y equals x plus 2 is our oblique asymptote. So when you go through the long division process and get the quotient, that's what your oblique asymptote is going to be in this case. Let's talk about rational inequalities. We solve rational inequalities much like how we solve polynomial inequalities. Remember, for polynomial inequalities, we moved everything to one side and then factored the polynomial and said that the only places where the polynomial can change sign is where the polynomial was equal to 0. So in that case, we created test intervals and checked test points and figured out the appropriate signs that we needed to solve the inequality. We're going to do almost exactly the same thing for rational inequalities. We're going to move everything to one side so we have 0 on the other. We're going to factor the top and factor the bottom. But for rational functions, it can change sign not only where it hits the x-axis, but it can also change sign when it crosses a vertical asymptote, where it's undefined. All right, so let's go through the procedure of solving rational inequalities. First step, just like for polynomials, move everything to one side. Second, combine everything into a single fraction on the side that's not 0, of course. Then factor everything in sight. Factor the numerator, factor the denominator, and find the zeros of both. Those zeros are where it could possibly change sign. After we find those zeros, we'll create a table of intervals, much like what we did for polynomial inequalities. The endpoints of those intervals will be all of the zeros that you found in the third step. Then again, just like what we did for polynomial inequalities, choose test points in each interval and check the sign of the rational expression. And then, of course, we're going to use the intervals that have the sign that we're looking for. Huge, 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 huge red flag. Do not do not clear the fractions. You have variables in the denominator when you're doing these. We cannot multiply both sides of an inequality by a variable because you don't know if the variable is going to make the expression be positive or negative, which means you do not know if you can flip the inequality. So again, I cannot stress this enough. Do not try to clear the fractions in an inequality involving rational expressions. All right. I emphasize this because in this example, it's very, very tempting to try to do cross multiplying, right? Multiply both sides by x minus 3, multiply both sides by x plus 2. That is the exact wrong way to start this problem. The correct way is to move everything to one side. So we'll subtract the 1 over x plus 2 to the left-hand side. Get a common denominator, so we'll multiply the first fraction by x plus 2 and the second fraction by x minus 3 on top and bottom, of course, because we need to multiply by a form of 1. We have 2x plus 4 minus x plus 3. So we get x plus 7 on top when we simplify. And then, of course, that's over x minus 3 times x plus 2. This now has everything factored. The numerator is 0 when x is negative 7. The denominator is 0 when x is negative 2 and x is 3. These will be our endpoints, and of course we want to consider them in order. So here's what our table looks like. Well, our first endpoint that we hit coming from left to right will be negative 7. Choose a test value of negative 8. Plug it into this factored form. It's much simpler if you plug it into the factored form because all we care about is whether or not it's positive or negative. Put a negative 8 on top, we get a negative number. Negative 8 into each factor gives you negatives. You've got a negative over negative times negative. That'll turn out to be negative. Next interval goes from negative 7 to negative 2. So choose, say, negative 3 as a test value. Top is now positive. Bottom, both factors are negative. Positive divided by what will end up being a positive is a positive number. Next interval is negative 2 to 3. Pick 0 for your test value. You get a positive on top. First factor is, got these backwards. The first factor is negative. The second factor is positive. This is, it's correct. It's just in the wrong order. It should be negative times positive. But in this case, we get a number that is less than 0. Finally, our last interval will be from 3 to infinity. The test value, we can use 4. Everything is positive, so the whole quotient will be positive. What are we looking for in this case? We are looking for negatives. We want the negative or 0 because it's less than or equal to. So notice that we can go negative infinity to negative 7. That's certainly a negative value. We include negative 7 because it makes the fraction 0. On bottom, however, we also have the interval from negative 2 to 3 makes it negative. But notice that we did not include either endpoint. Remember, the negative 2 and the 3 in this case came about from the denominator being 0. Well, that doesn't make the expression equal to 0. That makes the expression undefined. So I would not include negative 2 and do not include 3. In general, do not include any value that makes the denominator 0 because that makes the expression undefined.